Um,
There you go. Go ahead.
It sounds like a number of you are fairly new to data analytics. So I'm assuming that a lot of you aren't familiar with categorical encoding and things like Hot Encoding. Is that right? Is anyone familiar with the term Hot Encoding? Okay. So that works out pretty well for this presentation. The first half of the presentation shouldn't require you to have any previous knowledge of things like Hot Encoding, that we're talking about things at a theoretical level. If you are curious about the technical side of implementing it, it is fairly easy to implement. A lot of these solutions that we're talking about in Google Colab has the Python code I shared in the chat session. You can go and see the output of some of the Python code, and you could play around on that. I've got a backup of the code, so if you do want to play around with things, change some of the data, there's no harm in changing any of that. I've also got screenshots. I also put out the slide deck on a link to bit.ly for the slide deck if you want to browse around to different portions of the slide deck. So let's go ahead and get started. So I'm a data architect at SelectHealth, in the insurance side of Intermountain Healthcare, and we were working on a project that involving saving money for our members and being able to identify a number of different opportunities for providing savings. So we were doing predictions based upon some of the savings that we've had in the past. Can we repeat those in future instances that our members are encountering to provide them with additional savings? So there's a lot of numerical information that we're processing, but there's also a very significant portion that includes categorical features that have things like our members, that we have over 1 million different members, and representing them categorically and doing analysis on that can be quite challenging to find savings in meaningful ways. And what we really looked at is, initially we were trying to find out what was the likelihood of savings opportunity in a specific condition. If it was a claim or a visit, were we 10% likely to find savings in that event, or were we 90% likely to find savings in that event? And then how many occurrences of that occurred? So ideally, we wanted to find instances where there were lots of opportunities and a very high likelihood of being able to save people money. And we translated that into charts representing savings versus effort, or return on investment. That how much effort does it take in order to save our members significant amounts? So for this next part, this is interactive, and you can come off of mute, or you can vote for this in chat if you want. Oh, okay. And if you want, sorry, one bit before voting on that, the slide deck is available on bit.ly/encode big data if you want to download that. Okay, so this was where you could vote. Which of the T-shirts was the best rated off of, this is a theoretical, off of Amazon. If a T-shirt had a 5.0 rating, but only had one person rating it, if you had a T-shirt with a 4.73 rating, but 42 people had given it a rating, or C, a t-shirt with a 4.7 rating, but over 3,000 people rating it. Oftentimes on Amazon, if you're sorting it, you're going to have that 5.0 shirt rating at the top. And that was kind of a personal pet peeve of mine of it's easy to get 5.0 when it's only one person voting. So what are people's thoughts on what shirts they thought would have the highest rating? So you can click on the chat session at the bottom of the window to open up chat and add your vote in. Okay, Pat's got his vote in. Okay, pretty unanimously, we've got people voting for C. I think I biased that vote a bit, saying that was my pet peeve, but I'm in agreement with you there. And while we were looking at categorical encoding, we found a better way to be able to sort the ratings. And we're going to come back to that rating just a little bit further. We're going to be doing a lot of talking about t-shirts. We can't talk about PHI Intermountain related data, so we come up with fun things like t-shirts and how many shirts should we order for a concert. If you were an organizer for lots of concerts and you were ordering lots of different shirts and different sizes and different colors in lots of different countries, you wouldn't want to order a lot of shirts that you're going to end up having a surplus on. So you want to have some type of predictive capabilities to be able to identify what type of inventory for the shirt should you be ordering. So you could take a look at samples from a previous concert where you've got small, medium, large, extra large shirts, and you've got lots of different colors. The black and white shirts are really popular, and the extra large and large shirts tend to be more popular in sizes. But as we get more and more information about the demographics of our people that might be attending the concerts, we start collecting more data. So we might be interested in men's and women's sizes. We might have a concert that we know we have a significantly larger number of women attending or a significantly larger number of men, younger people, older people, different demographics from different countries. And we would want to adjust our orders based upon the demographics of the attendees. Well, it starts running into problems when you start building out these charts for all sorts of different combinations, all 100+ different countries, all of the different age groups, all of the different genders. Maybe you want to look at ethnicity, any type of demographic information that you can collect based upon the audience to be able to predict your sales. And it becomes an overwhelming amount of data that becomes difficult to handle. So oftentimes, what we do is we provide simple multipliers that are going to summarize the different values by coefficients. So we might take a look at things like 70% of the men attending a concert purchase a shirt and 80% of the people in Spain. All of these numbers are hypothetical with a little bit of background information that I was able to glean off of the web, but this is certainly not scientific studies. And then we've got the different styles of inventory of which shirt colors were the most popular, which sizes were the most popular. And by quantifying the information in simple percentages, we can represent a lot of different information without having to be overwhelmed by the data. We can just plug in the formulas. So what that could look like is we might have demographics from sales for different conferences or concerts in the past, where we've got demographics from people who were in Peru, who were male, teenagers, that they may have bought some black shirts in extra large and extra small. And when you add up all of those, all of the data for all of the receipts from your concerts, you develop a more and more accurate model. So we can get likelihood of a person with this demographics buying this particular style of shirt. There might be people with a very similar demographics might purchase much fewer extra small shirts. Then we can take the individual data, aggregate it across all of the groups over all of the receipts, and we can get those numbers saying, okay, 70% of the males purchased a shirt, 80% of the people from Spain, etc. And we can use that information to be able to build predictive models. So in the future, we could say, we've got some concerts that have 200 attendees with this demographic, and based upon the shirt sales previously, we're going to predict that they should have had 13 shirts in an extra large black ordered, no extra small shirts, and then a large number of extra large black shirts and even more extra large black with different demographics of people from Spain and Peru. So organizing the data in terms of in a similar style to this, where you've got ones and zeros, you could have this information filled in where you have different drop downs you're selecting for, do a pull down for gender, do a pull down for countries, pull down for Peru. Putting it in a database with a bunch of ones and zeros makes it easy to do a lot of calculations. So the calculation for the number of people who are male who bought a shirt, you're simply going to take the mean of that entire column. So in this case, it's 2 out of 6, which isn't 70% because we don't have all of the data that's available there. But if you took the average of that whole column, you would end up getting the numbers at the bottom to be able to fill in your coefficient values. And then you can use that information to be able to do a lot of your predictions. Similarly, you can collect the likelihood information for attendees. So that method for storing the information, rather than having a sales receipt that said, this person purchased the shirt and this is the size that they purchased, that they purchased an extra large, and maybe it's even more detail than that, that was also a red shirt and the particular style of shirt that they ordered. So ordering the information in this method called Hot Encoding, where you take each of your different categorical values, you give them each a column with the label of the category, and you simply add a 1 if it was true that in this case the receipt item was purchasing a small shirt. In this case, they purchased a medium shirt and a large shirt. In this receipt, they had 3 line items where they purchased an extra large and 2 extra large shirts. So you don't, even though you could put they purchased 2 extra large shirts, with Hot Encoding, you would represent it just as a 1 or a 0. I left the zeros out in these instances because it's a lot easier to read the data to see where the ones are if you didn't have the zeros cluttering the data. Normally you would have it filled with zeros rather than nulls. And you can use that information to, again, come out with these mean totals. This one's actually accurate, I believe, that this is 10% of the sales were smalls, 20% mediums. So it's easy to do totals, your total sales off of this, your mean sales. Having this unaggregated data makes future aggregated data even easier. So the advantages of Hot Encoding are that's really easy to understand and interpret this data. It's easy to filter on things that you can say, show me all of the receipts where there were small shirts. Show me all of the shirts that were red. That you can add those filtering options on really easily. It's also helpful with categorical encoding, you'll hear two terms that are passed around quite a bit, ordinal and nominal. And what those are is, ordinal is a category that has a particular order to it, like small, medium, large. There's an inherent order to that. Grade point averages, that you could have A is a 4.0 and A plus is a 4.25, B is a 3.0. That's easy to put in order to those categories. But oftentimes there are nominal values, like categories, like countries, like United States, India, China. You could order them based on the geographic size of the country, or you could order them based on the population or GDP, but there may not be an inherent order. So we refer to those as nominal. So things like red, blue, green don't tend to have a particular order that's apparent to me, at least. And it's also, one of the advantages of this type of encoding is it's very easy to reverse translate the encoding. If you've encoded it to ones and zeros, you can quickly see that this one is representative of a medium shirt, whereas some of the other encoding methods that we'll run into are not going to have that ability. And we'll take a look at the pros and cons of several different encoding methods. So there's a lot of different encoding methods, and this particular method called contrast encoding is highlighted by, or represented by, representing the categories as the number, quite a number of columns. So take the number of distinct labels within a category. If we have 5 shirt sizes, we're going to have 5 columns. And with some of these algorithms, we'll do one less column, which helps with our predictive algorithms, but becomes a little bit harder to translate. So in this case, if we left off this extra large column, we got rid of that column entirely, we could simplify some of our predictive algorithms, and we would know that this receipt was for an extra large shirt, because the record for the shirt would be completely blank, which becomes more confusing. So if you want to look at some of these others, you can look ahead further down the slide deck, or you can take a look at the Google Colab to see how some of these are calculated. With each of these, you're going to notice that they're a contrast encoding method, which means that they have K or K-1 columns, one column for each distinct label within the categories. In some of these, so the sum modification, that one's fairly easy to interpret. That last column is simply represented by a -1 values for the final column rather than all zeros. And then these other ones start getting a little more complex to start understanding. Backward difference in polynomial coding, I couldn't find any distinct use cases where they were particularly valuable or they had greater predictive capabilities than the other models. So I tend to recommend sticking with these top 3 methods for categorical encoding. And we'll take a look at some of those a little bit later on. Now, talked about some of the positives for contrast encoding. The biggest negative for contrast encoding is that it can generate too many columns. So if we have lots of different countries or different colors that we're representing, if we were representing countries, we would be adding 100+ different countries, 100 additional columns. And that runs into challenges with some of the predictive algorithms. It also becomes harder to view the data in a spreadsheet or database if it just goes on for columns and columns. With the health data, we were often having to work with categories that had lots and lots of different columns, like claim diagnosis or different procedures or member IDs can generate on the thousands of columns. So that really becomes unmanageable. And in some instances, you start running into memory issues with being able to process that many different columns. With R and Python, there are some ways to be able to work with those sparse columns that are filled with lots and lots of zeros, but it does become much more complicated to work with things as you start adding on the different columns. So one method that to get around adding all of the columns only utilizes one distinct column, and that's ordinal or ordered categories, which I had mentioned earlier. So one method for doing that would be you take all of your shirt sizes and you simply order them from small to large and give them a number assigned to them. So within your database, you would simply replace any instances of extra small with a 1, any instances of small with a 2. One of the immediate disadvantages you see to that is you can't do immediate calculations off of that. If you start doing a sum or an average of these numbers, it's just not informative. But it is helpful for the different predictive models that you can see are extra large shirts sold more often than extra small shirts. You could also do this with different age groups. So if you had groups like teenagers, adults, and seniors, you could assign that a label from 1 to 3. And there is also a categorical encoding method called label encoding, where if you took nominal data that didn't have a particular order, that would be referred to as label encoding, where you assign a number to different categorical values. And disadvantage here is that you're now implying a number, that you're implying that black is greater than green. You're implying, or possibly a reverse order. You could be saying USA is number 1 or USA is less than New Zealand. So you want to be very cautious about using label encoding because it could be implying that ordered size. There's some workarounds for that. If you're working with some of the tree-based algorithms, you can say this column is a categorical column. So don't treat it as a numeric value, treat it as a category. But again, still becomes confusing, and if you forget to set that, you can end up with trouble with your algorithm. So an alternate to the encoding method, the ordinal or label encoding method that only uses one column again, is to use target or mean encoding, where you simply take the average of all of the various columns, all of the various categories that you're trying to represent, come up with a percentage and assign that percentage to each of these areas. So In this case, it would be a percentage representing the size of the shirt. That 10% of our shirt sales were smalls, 30% were extra larges, and you can use this for your predictive algorithms very easily to be able to say, I'm trying to predict how many of a particular shirt I should be ordering. Well, 30% of your shirt should be extra large. You simply replace, instead of adding a column for each of those shirt sizes, you might have for each receipt, you might have a small, medium, large appearing on the receipt. And when you go to do predictive analytics on it, you would replace that text with a number. Then you could run your algorithms on that. It becomes difficult to reverse translate that. So if you sold the same number of large and extra large shirts, you couldn't translate 30% back to clearly being large or extra large. So you lose a little bit of information if you start encoding using that method, but very, very powerful in a number of different ways. And we started using this method for doing a lot of our analysis and found that we were able to do predictions with a much greater degree of accuracy using this method. It still runs into some shortcomings that we'll talk about in a couple of slides. Another advantage to the target encoding is you could represent multiple targets off of each type of encoding. So you might be losing some of the information, such as extra large and the medium being 20% of the inventory sold, because we can't reverse translate it. You could start encoding additional information. So instead of having just one column representing your target and mean, you might have two columns. So you might have a column representing the inventory sold. If we sold 100% of our extra smalls, so we're good there. We also have a column for the number of returns. So if we're trying to predict returns or some other categories, we can identify which colors are being returned more often. Maybe our red t-shirts are bleeding in people's laundry and people hate ideas like that. Maybe you're going to encode the rating for the t-shirts. So you could have a column that's representing the 1 through 5 star ratings for the various sizes. And you can predict which of the t-shirts people are rating more highly. So putting that all together, this just happens to be a slide that I had found off of rush order tees of based on their experience when you're ordering 100 or more t-shirts. This was the distribution. A lot of large t-shirts, very few extra smalls, and a few triple XLs. So the challenge that people run into with target encoding is overfitting, and we ran into this in a big way. And I'll tell you a little bit more about some of those examples of where we ran into overfitting that really created problems with the predictive analytics we were running. So if you remember back on this slide, we sold 100% of the inventory sold. We only 1% of our shirts that we ordered were extra small. And we sold 100% of those shirts. So when we're ordering shirts in the future, if at the first concert we had 2 extra small shirts that were purchased or that we stocked, and 100% of those were sold. If we run that through a predictive algorithm, what would that tell us about how many shirts we should order in the future? If we ordered a million extra small shirts, based upon that simple model of having sold 100% of them, it would predict that we had sold a million we would be selling 1 million extra small shirts, and we would likely end up with a lot more extra smalls than we needed, and we'd be selling them at a super discount just to get them out of our warehouse. So to solve that problem, the challenge that we ran into was for very small sample quantities, similar to that T-shirt rating of if one person rates the shirt, if they rate it a 1 star, it's going to give that T-shirt a 1-star review. If they rate it a 5-star, it's going to give it a 5-star review. So what we want to do is we want to reduce the impact of low numbers of people contributing to a particular category. Low numbers of instances of a category should have a lower weight than something that has a high number of instances. So we use there's a couple of different techniques for this, but they call it shrinking, blending, or smoothing to be able to take predictions where we have just one entry or one record representing the overall score compared to, in this instance, 10 different records representing the percentages. We want to be able to shrink that number down, that give it less weight if it has just one record representing it versus 10. And one method that we can use to do that shrinkage or blending is to add a vote to each of the different categories representing the mean. So in this, it's a very simple calculation of all of these have a mean or average of 50%. So for each of these categories, where this category we had one record with 100% target score on it. If we add one vote, or I'm sorry, this instance is adding 3 votes with a target score of the mean, which is 50% here. So we add 3 votes of 50% to 1 vote of 100%, and that's going to end up, seems like that number, I was expecting that number to be a little bit lower. So what's the average of 100, 50, 50, 50? That's 250 divided by 4. So that's a little bit less than 80%. So that's accurate. The other way that we can do this is if we added 7 of the average or mean proxy votes to it, we get even more shrinkage toward the mean. So that moves that score with just a category with just one record even closer to 50%. So they end up getting more of an average vote. Whereas if we've got 10, we're not doing very much of the adjustment to the score, that we're moving that 0% up to about 20%. And if we had even more records, it would reduce it even more. So another way to look at this is if our data was skewed, if our mean average was closer to 85, 90%, it would also shrink that toward the mean if we're adding in some proxy votes for you could think of this as the T-shirt rankings on Amazon, that fewer quantities that we have, the less it's going to deviate from the mean. And the more votes that we have, the more true to the actual numbers it will be. So looking at this in terms of, this is still a hypothetical graph here, but in a distribution with a mean of 50%, when we run into a lot of samples, when we're running into samples with thousands of different categories, we often and the distribution of the rankings is spread out between 0 and 100%. It's really common when you have one vote, you're either going to have in true or false instance. So this might be COVID testing. If you tested positive for COVID or tested negative for COVID, it's either going to be true or false. So if you have one person with a COVID test, you're either going to get a 0% score or you're going to get 100% score off of that one person. If you had 1,000 people that were getting the test, and let's say we know that COVID positivity is not going to be 50%. With 1,000 people, the averages are going to be closer to the mean. That the numbers will start getting closer and closer to the mean, the more records that we have. Trying to think of an example that I can use where I'm not revealing too much in the way of PHI. So when we do various demographics, when we're grouping people together for COVID, if we had the country that they were from, most of the people that we're testing here are from the United States. So we're going to have a lot of samples of that. We might take a look at someone got a test from New Zealand, and we had only one person got a COVID test from New Zealand. They would either have 0% or 100% of the people from New Zealand tested positive for COVID. Well, if you look at that information by itself, it's like the extra small t-shirt order of 2. You don't want it to say things like 100% of the people that we tested from New Zealand were positive for COVID. So we want to take a look at what is going on with the people from New Zealand, or 0% of the people tested positive for COVID. So what type of immunity do they have? You don't want that type of knee-jerk reaction to be occurring when you have those really small sample sizes. So when you add in those proxy votes, you will particularly eliminate that 0% and 100% categories, that you start moving those outliers in closer to the mean by adding in those proxies. And then if you look at the far side of things, you're not going to get very much adjustment at all, that you can clearly see these two categorical values were hardly changed at all within this representation. The quantities of 1, instead of being at 0%, that 0% record got moved all the way closer to about 45%. So we ran into a number of different analytic situations where we had lots of occurrences of things like 94%, means of 94%, which meant that we had a lot of different categories that qualified as being 100%. And the reality, especially in medicine, is it's very rare to have a situation where it's 100% of the instances of a particular situation are actually true. It's usually just a problem with a smaller sample size. As we move toward categories with much larger sample sizes, we get numbers that are close to 100%, but very rarely do we find a category that is actually a true 100%. So that same method of adding in those proxies for the medians reduces the likelihood of being at 0% down here or 100% up here. And we can trust the data, samples of the data, a little bit more with using this method for target encoding with proxy voting, or referred to as smoothing, blending, or shrinkage. That's just a close-up of the some of the numbers. This particular chart is using hypothetical samples again, rather than any real records, but you can see we still had a couple of 100%, and adding in the proxy votes just moves that hair under 100% for those votes. It's a little bit more on shrinkage and blending. So there's similar to contrast encoding, there's a lot of different techniques for target encoding. The target encoding is typified by you're using your end results to predict your current, to help build your predictions. But if you're using the end results to make the predictions, that's a sure sign that you are likely going to have run into problems with overfitting, meaning you need to come up with a solution like shrinkage and blending to avoid those 0s and 100%, and give less weight to records with much lower representation. If you're taking an average of the people in South Jordan who like 9-inch nails, that's going to be a lot different than the number of people that are interested in 9-inch nails over the United States, and even more significantly different if you did a worldwide population. So the higher quantities, you're going to get more accuracy. The lower quantities involved in a prediction, you're going to get lower accuracy, and you're wanting to add in, sometimes it's referred to as adding noise to the prediction to avoid overfitting, and particularly reducing the impact of data that you're not quite as sure about. So most of these different encoding methods are relatively easy to understand. Leave one out encoding says do a target encoding, but don't include the current record when you're calculating the target. That's going to add in some noise to your prediction. Category boost encoding is very similar to leave one out. It simply says any records after the current record, ignore those, as well as ignoring the current record. So that's adding in even more noise. And what you'll see is cat boost encoding has scored very well in Kaggle competitions. Is anyone familiar with Kaggle competitions? Has anyone heard that term before?
Yes. Yeah, I have.
So Pat's heard of those. So particularly those that are taking classes, one of the interesting exercises if you're going to go into predictive analytics is to compete in a Kaggle competition, which is a worldwide competition trying to solve predictive problems. And what they do is they put out a data set and they say, how would you predict these particular outcomes? So you get access to some great data sets. There's hundreds of different projects, and there's several of them that have the competition's already completed, and you can go in and you can look at the results. How did they get really high predictive results? And with having data scientists from around the world competing on these, you get lots of different inputs, people solving problems that they might not be exposed to. People in the medical field might be predicting T-shirt orders for concerts. Um, there were a number of healthcare related exercises. Big Data Utah has, or Utah Geek Events has done a number of local data competitions. The Bike Utah data competition, there was a climate or air quality predictive. I'm gonna speak wrong to this. So Pat knows it well, but so one of the teams that won one of the predictive competitions was on air quality in the Salt Lake community. And one of the things that they noticed as a result from that competition was that if we drive less, then the air quality should improve within Utah. And one of the findings that they had was, well, we all know, or many of you who are new to Utah will soon find the roads are a lot easier on Sundays in Utah, that there are many fewer people on the roads on Saturdays and especially on Sundays. So there should be an improvement in the air quality on Sundays. And when they looked at the analysis, they found there wasn't an immediate improvement. So they realized instead of day-to-day changes, what you really want to do is you want to do changes in air quality over several weeks. So when you see that they're able to predict that inversions are coming in the next several weeks, and they start putting out the signs on the freeways saying, encouraging people to drive less, not for a particular day because the inversion is bad, but drive less because there's an inversion that's going to be coming. So if you start carpooling on those days, you're going to have a greater impact by carpooling for a couple of weeks rather than carpooling or taking mass transit for just a day. And that, of course, ran into some challenges with spreading the word about how things got political beyond just the science and how things were interpreted. So always some caution on predictive analytics to your predictions may have ramifications far beyond what you're seeing. So that comes back to the T-shirts, how to vote for the various T-shirts and ratings. So a method for being able to sort the Amazon T-shirt orders in a more helpful manner than 5.0 being rated at the top would be to add in the additional proxy rankings. So if we took a look at, this is all hypothetical, if the average ranking on T-shirts was 3.52 and we added one ranking to each of these T-shirts with the ranking and the number of rankings, we can see 5.0 T-shirt, there was one person who ranked it or voted 5.0. We're going to take that 5.0 at a ranking of 3.52, and that comes out to 4.26, halfway between 5.0 and 3.52. The way to do that is multiply the number of rankings by the number of T-shirt sizes and multiply the proxy ranking by the mean. So 1 times 5.0 plus 1 times 3.52 over the quantity ranked and the quantity of proxies comes out to 4.26. So the 4.73, similarly, you're going to take the real ranking times 42 votes plus proxy ranking times the mean, and then divide that by 43, the real rankings plus the proxy vote comes out to 4.7. So it's a tie between B and C. So the art to this type of encoding method is how many proxy votes do you add in? And this becomes more of an art than a science situation. So if you had a 50 proxy votes coming in, instead of the 4.7 vote or 4.7 ranking for one person, one proxy vote, for 50 proxy votes, adjusted back to 4.07. The impact to the 4.7 vote with 3,000 rankings is a very small adjustment, going from 4.7 to 4.68. Whereas when you had just one proxy vote, it hardly changed at all. I should have grabbed myself a glass of water. So I'm going to start wrapping it up here and want to give you an oversight of some of the additional encoding methods. If you want to explore them further, I'm going to just discuss some of the different material that's available in the next slides without going into detail on them. So with the various, there are lots of different categorical encoding methods. These are methods that are available in Python, and there are some side notes on coding methods that are available with coding examples in R. So how do you pick which one to use? First of all, if you're not using categorical encoding, these don't apply. So if you're dealing with currency or time, percentages, numeric values, you oftentimes aren't going to use any of these methods. The exception to that would be things like zip codes are categorical, even though it's a number, it's still categorical in nature. So you may want to look at categorical encoding from there. Then look at, is it ordered? So use an ordinal technique. If not, use a nominal technique. And then it starts going through various methods. If it's less than 4 distinct categorical labels, then you want to use one hot encoding is simple, and I would say just go for it. And as it starts getting more complicated, start evaluating it further to see which other alternates you might use. And there's some techniques involved in being able to blend the different encoding methods together. So the flowchart is an initial encoding method to take a look at. You can often find that you get reasonable results with the encoding mechanism that recommends, but you'll find, using a similar encoding method, you'll find more accurate results as you work through some of the other algorithms. Okay, and then this is a summary of the various encoding methods, whether they're contrast encoding methods or target encoding methods. Contrast encoding methods, that's when you have those K columns. If you have 5 t-shirt sizes, you're going to have 5 columns of encoding. Target is you're just going to have it encoded into 1 column, and it's going to use the predictive results, your dependent variable, in order to predict your final results in doing your encoding. And these various asterisks here are identifying references that if you want to find out about a particular method more, you can look at the references listed on the next slide to find additional details. And understandability is my interpretation of how easy is it to understand? One hot encoding is easy to understand, whereas Helmert encoding is, if you're good with linear algebra, hey, have a field day, but it's been a couple decades since I've used linear algebra regularly, so it's tough for me. So these are the various reference guides. There's Python coding examples, there's R coding examples, and a number of great articles on categorical encodings. One of my favorite is listed at the bottom here, is just a well-written, simple to understand method or article rather. And the various considerations, I'm not going to go into these right now, but as you're looking at different methods for doing the encoding, some of the things you want to think about, such as how many of the distinct categorical labels are included in the set, and some additional details. The common definitions that you're going to run into, I've mentioned K. K is the number of unique categorical labels, and you're going to get lots of different terminology that means the same thing. So categorical values, categorical labels are all the same thing. N is the number of records that you have. So for this example, where we've got red, blue, and green, we've got records starting at 0 and 9. We've got 9 records, so N is equal to 9. The dependent variable that is the outcome that you're trying to predict. In this instance, 0's being false, 1's being true. And you'll have terms like group mean. So the mean or target value of blue, we've got 2 instances of 1s and a 0. So that we've got 3 records, so 2 trues out of 3 records. The group mean is going to be 2/3 or 66%. And you'll hear the term global population mean, which we've got a total of 5 1s here, 5 trues out of all 9 records, that n value of 9, so 5/9 is 55% for the global mean for the whole group. So we use the global population mean to add in the proxy votes to smooth out our target encoding. And there's various examples in Python. Google Colab is fantastic for, it's very similar to Python notebooks, IPython notebooks, and there's some other terms for it, where you can do your coding, you can run the code and see the results of the code all within one page. It's available for free. I think that they might also have some R coding examples. And in this instance, we use that data set I just looked at with 9 records of red, blue, and green. And we do the one hot encoding. So this is, to do one hot encoding, you just need to do 2 lines of code to implement it, and you import 4 libraries. So it's install the category encoders library. So that's 1 line of code, 4 lines of code to import the libraries, just 2 lines of code to get the results, where we've got ones here are color 1, which is red, color 2 is blue. We've got 3 instances of that. Color 3 is green. We've got 4 instances of that. And over some of the pros and cons of those, Sun encoder is very similar, that you've got red here, green here, and then the negative ones, instead of using another column for that 3rd color green, you're going to represent this with -1. And it the predictive algorithms have an easier time with this type of encoding of the data. Ordinal just puts an order of red is ones, blues are, we've got 3 2s for blue, we've got 4 3s representing the greens, and this again is implying an order to your categorical encoding, which you probably don't want for colors. So not the best solution there. And various other algorithms you can take a look at. So binary, BaseIn, and hashing are all methods with the idea of one hot encoding uses too many columns and they use a reduced number of columns, but you lose the ability to translate back with some of those. The last one I didn't mention for is frequency encoder or count encoder is how many of a particular instance. So there's 2 instances of red, so that gets encoded as with 2s. Blues are 3. If there were 3 instances of green, that would be encoded the same as blue as 3s. And this becomes valuable for T-shirt size encoding. That's really very similar to frequency. Frequency encoding is the number of T-shirts that are ordered. That ends up becoming very similar to your target encoding. And so the target, with the target encoding, you can see half of the, well, target for red is 50%, so it comes out at 50%. For blue, 66%, and for green, half of them are true, half are false, so that's again back to 50%. That's when we turn smoothing down to a really small value, and if we have smoothing equal to 2, meaning adding in 2 smoothing or 2 proxy votes, then you get numbers similar to this. Maybe that may not have been true for number of proxy votes, but increasing the smoothing will move the numbers closer toward the mean. Okay, and some examples of how to calculate some of the other mechanisms. M-estimate encoding is really, that's specifically saying M equal to 1. It's saying add in 1 proxy vote. M equals 100 is saying add in 100 proxy votes. So you can see here where M is equal to 0, we get that same thing as target encoding. So target encoding without any smoothing. And James Stein, really good results off of James Stein encoding and Helmert encoding. If you can understand that, well, anyone want to offer to explain that? It was all Greek to me. Okay, and weight of evidence is categorical encoding method that people used for computing credit scores. So, and there's a couple of these that I haven't found use cases for. That's the Google Lab code. If you wanted to see just the Python encoding examples, so all of the code generated for that is in 3 pages. To represent all 15 of those encoding methods. And some of the additional reference slides. I don't think that has, oh, okay. And then this chart also throws in supervised learning, if which methods use supervised learning versus unsupervised, which almost correlates to target encoding. Okay, and I think that is all that I had. So again, if you're a Python coder, there are examples of the Python libraries that you can use. with some explanations, and the R methods, there's coding examples for R for most of those categorical features. So that is all that I had. Welcome any questions. Realize that Paul and Michelle, that this may be a new area to you in a number of different regards. So you're welcome to ask any questions that may have come to mind. I don't expect you to be insightful on a technical aspect of this. So definitely the no question is a dumb question at this point, and Pat is also quite knowledgeable about a number of areas. And if you happen to know how to translate that Helmert encoding, well, hey, I'd love to hear it.
Doesn't sound like we have any questions.
All right.
Well, either so also, just so everybody knows, the slide deck link is in the Big Mountain Data, the Big Data Utah comments. So it's there on the meetup. And as soon as I get this recorded and put on YouTube, which, it just processes, I'll put a link to this on YouTube as well so that you can watch any part that you wanted to go back over. Okay. Thanks, everybody. Thanks, John. Appreciated the presentation. Loved it. Really appreciate you coming out and helping us out and stuff. And so for everybody else, we'll definitely see you in April. Like I said, there's another presentation coming up. I should be able to announce it in the next few days, and it'll be at a similar time.
Fantastic. And looking forward to being able to connect with people more in person.
Yeah.
I think it'd be a great opportunity, especially with so many people in South Jordan would love to be able to connect with people. And there are a lot, there is a big, so Michelle, are you new to Utah?
No, she's in Bellevue and she's in Washington.
You're in Washington. Okay, that's right. Okay. So, and Paul, were you at Zion Bank?
Yeah.
Okay. Okay, so there's lots of great opportunities for connecting with people through the Utah area, especially. And Michelle, if you are interested in coming out to a great conference, the Big Mountain Data Conference has been a really spectacular community conference that oftentimes a Friday and Saturday event that fantastic opportunities to meet people, and the hallway conversations become incredibly valuable to learn a little bit in the sessions and then hear about how people are implementing various solutions and what are some of the real world shortcomings of different solutions and the wins with different solutions. It's always better to hear from people who have used the products than to hear from a sales rep that has been talking up various solutions.
Yep. Okay, well, thank you, everybody. You have a great night. Thanks, everybody.
Okay.